Hello everybody, it's a pleasure to welcome Christian Lindgren from the University of Gothenburg, Chalmers University of Technology. Christian did his PhD in '88 and he was also one of the people who were recycled through Nordita as a fellow back in between '89 and '91. And he moved then back to Chalmers as a postdoc assistant, but then became associate professor, and is now, since 2006, full professor and professor in complex systems. He has worked extensively on various aspects, including pattern formation, evolutionary modeling. That's what the work included that he did at Nordita back in the early 90s, and he has been working on information flows and cellular automata. But in the recent years, he has been involved significantly in environmental science and energy systems. But today he will be talking about another aspect that he has been involved in, namely over the last 4 years, he has been part of a big EU project which is called the PACE project, which stands for Programmable Artificial Cell Evolution. And so this is certainly a very exciting aspect of possibly making artificial life at some point in the future. And so as part of this work and in connection with theoretical aspects, he will be talking today about self-replicating patterns in information dynamics. Christian, please.
Thank you very much for the kind introduction, and thank you for inviting me to give this presentation. During the talk, please feel free to interrupt and ask questions if there's anything that is unclear or if you would like me to clarify anything. So, as Axel said, I will talk about self-replicating patterns and information dynamics. And this is one of my dear topics. Actually, I started to work on this already in my master's thesis in '83, and it continued through the PhD studies, where the title was Physics and Information Theory. And later on, I have been working on it now and then. And as Axel said, during the past 4 years, this has been my contribution to the PACE project, which is sort of an artificial life project in Europe involving scientists from anything from chemistry to computer science. The PACE project has a long-term goal to create artificial cells. This is not a goal that will be sort of fulfilled within the project's time, but within the project one is examining various ways to realize in chemical systems different components that in the future can be part of an artificial cell. My interest in the PACE project is the study of artificial chemical systems that possess lifelike behavior. And the type of lifelike behavior that I will exemplify today is self-replication. And that will be done in the context of pattern-forming chemical systems. So that will be one part, and I will discuss a specific type of chemical microfluidics reactor that is being developed in the PACE project. It's sort of a lab-on-a-chip reactor, and I will discuss to some extent how we have looked at models for self-replicating patterns and to what extent they can actually be implemented in this type of microfluidics reactor. But this is a purely theoretical study that is really in its first steps right now. The other part that I will present that will use these types of pattern formation processes as an illustration deals with the concept of information and to what extent we can use information to characterize what is happening in the process of pattern formation. The point in using information for characterizing pattern formation is that we can connect the information quantity with physical quantities like free energy and entropy. And in that way we can connect an information theoretic characterization of pattern formation with the thermodynamic constraints that the system has to obey. So there are these two things that I would like to discuss. Pattern formation, of course, is something that we find in lots of systems in nature. These are pattern formation on skins of animals, and so in a way these are self-replicating patterns, but this is not the type of self-replicating patterns that I'm referring to. I will discuss self-replicating patterns that are objects in themselves and that can replicate as such objects. Here we have the self-replication of organisms that on them have patterns of various types. But I will start with a discussion about some events or some findings in the history of primarily the theory of pattern formation that have influenced my research. I mean, there is, to start with, the classic paper by Turing in 1952, where he proposed a mechanism in reaction diffusion dynamics that could actually account for why we get the symmetry breaking in morphogenesis, where, I mean, in the division of cells in an embryo, that we can actually get cells developing into head and tail, for example. So that was the demonstration that fairly simple reaction kinetics with diffusion can give rise to pattern formation in an embryo. And he exemplified that by the type of stationary pattern being formed in a reaction diffusion system, which then is usually termed the Turing pattern. It did take quite a long time, though, until the first experiment was done where the Turing pattern was observed. It was actually not until 1990. Usually one thinks that this was observed earlier, especially when you think about the fairly well-known Belousov-Zhabotinsky reaction, where you do get spontaneous pattern formation starting from a homogeneous state. But the Belousov-Zhabotinsky reaction do not produce stationary waves using the mechanism suggested by Turing. But on the other hand, I would say that the type of patterns shown in the Belousov-Zhabotinsky reaction, which involves, for example, spiral waves, are highly interesting from a biological point of view. And our interest in pattern formation is sort of an evolutionary one. I mean, if one could have patterns that self-replicate, or patterns that can also, to some extent, be robust against mutants that possibly could start to be parasitic towards the dynamics in the patterns, then we could have some effective evolution in a population of patterns interacting. And one early theoretical study taking this question seriously and creating models for it was one by Borlist and Hocheweg in 1991, where they put the hypercycle model on a two-dimensional system. That model then creates spiral waves, and what they noted was that in that system, if we have mutations or if we have the introduction of parasites in these chemical systems, that is, parasites that exploit the dynamics of the hypercycle in a way so that the spirals actually are getting destroyed. Because of the structure of the system, having lots of spiral waves being placed out in the system, the parasites are not being able to spread. So the parasites are sort of confined within a single spiral, and the whole system can survive because of this mechanism of spirals to be protected from parasites approaching from the outside, so to say. Also here in Stockholm, Kronlund and Blomberg studied this type of phenomenon in similar types of systems. I would say though that it's still sort of unresolved whether this applies to real chemical systems. Now, spiral waves is one example of sort of localized spatiotemporal structures in pattern formation that is of interest to study from the perspective of lifelike behavior in chemical systems. And but I will, in the next slide, show an example of an experiment that turned out, or that was found in the beginning of the 90s, that show on a much more interesting phenomenon from the life perspective. And that is what is called the self-replicating spots experiment. So this is an experiment that is performed in a two-dimensional setting. It's based on an iodide ferrocyanide sulfide reaction. I'm not a chemist, so don't ask me exactly what is happening in this experiment. The setting is the following, and I'd like to describe it a little bit in detail because our interest in the PACE project would be to see to what extent can this experiment or this type of phenomenon be brought over to a microfluidics setting. So this experiment is slightly complicated. In here we have a two-dimensional gel in which the whole reactions scheme is taking place. Then there is a membrane between the gel and a stirred tank reactor where we have sort of the fuel for the whole chemical process. So there is an inflow of the fuel that drives the chemical pattern formation process going on in this direction. And this is a relatively complicated setup. And in the PACE project we would like to investigate whether one could make a more simplified construction of the reaction architecture and still have the interesting phenomenon that they did observe in the beginning of the 90s. And the phenomenon was the following, that you could observe in this two-dimensional system localized concentration peaks that has this temporal phenomenon that the peaks stretch out in space and divide. You see the division occurring there. There it has happened. There's another division going on over there. So this is an interesting example of that we have self-replicating of mesoscopic or macroscopic objects without having the protecting container of a membrane or a vesicle, having the usual biological systems with self-replication. It would really be interesting to see whether one could have a chemical system that have both self-replication and maybe also evolution even before we have the container that protects the objects that undergo evolution.
Excuse me.
Yes?
When you say self-replicating, what is it that is replicated here? It looks to me like it just splits off into pieces.
Yes, that's correct. So in the concentration peak, I will in a few minutes describe a model for it. But this is a concentration peak of a molecule that self-catalyzes its own production. So in a sense we have an aggregate of those molecules. And whether you want to call it self-replication or not, but you do have objects that are characterized by the presence of these self-catalyzing molecules. So you get, starting with one such object, you get two objects. So in some sense there is at least self-replication going on. And also you could also think of this system where you have a large number of concentration peaks in the system, and you have a mutation of this self-replication molecule within one of the peaks. That molecule, if it's successful, may take over the whole concentration peak to form now a new object consisting of a new self-replicating molecule. So, and in that way I would say that we have had a mutation that creates a new macroscopic object, but that is also capable of self-replication in that sense, yes.
What is really the conceptual difference between such a problem and bubbles that come when you boil water? You also have bubbles, and they divide into smaller bubbles, and you get more bubbles, and that's also replication.
Okay, I agree. That's a fair question. But in this setting, you could, in principle, consider, the possibility that the elements of these objects could mutate into something new. So you could say that you have some kind of genetic material, roughly speaking, that determines the properties of these objects. So these objects are concentration peaks. The properties, how stable they are, how fast they divide, are divided by the properties of the single self-replicating molecules. So I would say that is a difference from the setting of bubbles. We can get back to that later on. But okay. So at the same time as this experiment was presented, they also developed sort of a phenomenological model using reaction diffusion dynamics that reproduced the same type of behavior. And this model is the one I will use for illustrating the information perspective that I will put on this system in the coming slides. This is the development and the first investigations of the mathematical model was done by Pearson at Los Alamos, and this is a flora of the different types of patterns you can get out of this model that I will show in a few minutes. It ranges from highly dynamic patterns of the wave fronts moving through the system to fairly stable patterns looking like fingerprints, or to patterns here which are those self-replicating spots or self-replicating concentration peaks. The model looks as follows. It's a highly simplified model. I mean, the real reaction scheme, if you would like to model that, should involve tens of different types of reactions and components. But this is a highly simplified model, and it's sort of interesting that this simple model can recreate such a vast variety of spatiotemporal and stationary phenomena. So the setting is the two-dimensional system. We have an inflow of a component that serves as a fuel for the reaction, and the main reaction is this self-catalytic production of the B component out of the fuel U. There is also a decay reaction where the B component decays into an inert molecule G. And this we naturally model using reaction diffusion dynamics, and the behavior when we run it, you start with a concentration peak of B molecules initially. All the time we have the perpendicular inflow of U molecules that are driving this system, and we see here clearly how the concentration peaks stretch out in space and divide up into new peaks to form this sort of lifelike pattern of population of, I would call it, replicating concentration peaks. We also see that there is some instability of these peaks, so when they die, they leave room for other peaks to continue their division. So it's a highly dynamic system, and I think this system also illustrates to a large extent the possibility to have lots of different types of dynamics depending on what level you observe the system. I mean, on the molecular level you have very simple dynamics, the reactions and the diffusions going on. And then you can aggregate those reactions to this description of reaction diffusion equations. On the next level you have the concentration peaks that have their own dynamics oscillating and splitting up. And on the even higher level you have population dynamics where you can study how the number of concentration peaks vary in time. So there are lots of different levels you can study this system at. So what I will try to do next, sorry. The next step now will be to, I will get back to the dynamics later on, but the next step is to describe for you how one can use the concept of information to characterize what is happening in the pattern formation process, to characterize at what positions in the system do we find information, at what length scales in the system is information found. And just very quickly reminding you about some of the basic concepts of information theory that I will base this framework on. So we start with the basic concept of information, which is the information gained when you observe a specific event or you observe the system to be in a specific state I, being log 1 over the probability for the system to be in that state. And if P of I is the probability for having one of the sides of throwing a coin, being 1/2, then we see that the information is log 1/1/2 being 1 bit of information. In many cases you may be interested in the average amount of information you gain, or expected amount of information you gain when you observe the system. And then you take this, the logarithm of observing the state, the logarithm of 1 over the probability for observing the system in specific state I, and average that over the probability distribution describing the system. This average information gain when observing the system is called the Shannon entry of the system. Now, the quantity that we will use most for this framework is the relative information quantity, which relates to a situation where you may have an a priori description of the system, represented by V0, and then you make an observation or you learn something about the system, which does not reveal exactly which state the system is in, but reveals that there is a better way to describe the system using this probability distribution instead. Then it turns out that this quantity, the relative information, captures the information gain you get by replacing P0 with P. And this is always the positive quantity. So this is the quantity we will use in the information characterization of patterns in chemical systems. Now, there are many approaches you can take when you talk about information in chemical systems. It depends. I mean, the information quantities on the previous slide will, of course, depend on what are the probability distributions you use. What are the level of description that you will use for your system? So there are at least 3 sort of levels that one could consider. One type of information perspective is the information on what is the dynamics in the system, what are the reactions, what are the molecules involved. So this I would call the genetic information, telling you exactly what is the whole reaction scheme of this system. This is a pretty small amount of information, relatively speaking. The second, but also very important information perspective is the one coming from the information in fluctuations. If you have a pattern-forming system, fluctuations are crucial, of course, for determining exactly which pattern out of the whole class of possible patterns that will be formed. So there is this information flow from fluctuations up to the macroscopic levels where you sort of detect or observe the pattern in the system. Then there is a third quantity, which is the one that we will use, which is the information in the free energy that that is stored in the system. So this is better called information capacity. And this is then directly related to the thermodynamic constraints of the system. So using this quantity means that we will have a direct connection between the information characteristics of the pattern and the free energy that is stored in the pattern, but also the free energy that is required for building up the pattern. And typically, this energy quantity is much larger than the other two. So we will use a macroscopic description of the system and put that into the information theoretic quantities. And we will use the concentrations as the sort of the probability distributions in this description. So we have Ci of x being the local concentration of molecule I, and Ci0 being the equilibrium concentration of molecule I. So Ci0 would represent our a priori guess of what concentrations we will observe in the system. So typically we should expect to observe equilibrium, but then we make the observation of the system and we find it to be in a specific state, Cix, where x then may vary over space, or the concentration may vary over space when x is varying. And we put that into the Kullback information term, and we integrate this over the system to get a quantity that we can call the total information in the chemical pattern. The thermodynamic context is then the following. We consider now, of course, an open system. So we have the chemical pattern here that we would like to characterize using information theory. This system is all the time driven by an inflow of the U molecule in this Gray-Scott model that I showed before. And there is an outflow of the waste, that is sort of the products of the reactions, heat, etc. And we can maintain an out of equilibrium state, or even push this system further away from equilibrium by exporting more entropy than what is created and imported. And I mean, the connection to thermodynamics we do have in these outflows. We also do have it in the entropy production that is taking place within the system. So those are sort of the physical constraints that we would like to connect to what is happening with information within the system. So the goal now is to use the total information of the chemical pattern, to decompose that into contributions from different positions and different length scales, and see how that can be connected to the inflow of free energy, which can be seen as an inflow of information capacity, and the destruction of information that is going on all the time due to chemical reactions and due to diffusion. I mean, diffusion and chemical reactions typically tend to destroy information, even though, of course, chemical reactions in this case, having this self-catalytic nonlinear component, also, at least at some places, create information locally, or at least transform the information capacity in the free energy into some information stored in the pattern. And this is then just the relation we have between, so in here we have the total information of the system, and if one multiply that with Boltzmann's constant times temperature, under certain conditions this is directly equal to the free energy of the pattern. Or if you put it in this way, it's the work that is required to create this pattern out from an equilibrium system. So we have this relation that one bit of free energy, one bit of information K, because of Boltzmann's constant times temperature being very small, corresponds only to 10 to the minus 21 joule. So one bit of information is really very little in terms of free energy. So the step we are going to take now is to use the information theory concepts in what we call geometric information theory to show at what positions in the system and at what length scales do we find information. And we do this by starting to introduce a resolution or a length scale with which we observe the system. So we introduce a parameter R ranging from infinity when we view the system as being completely smeared out to R being 0 when we view the system with perfect resolution. And we form these resolution-dependent concentration descriptions by taking the convolution with the Gaussian with width R. So this is an example then of observing a chemical system with some spatial pattern, but without having any, having the worst resolution whatsoever. Still, what we can see when we observe it with the worst resolution is the average concentration. So we may already, at this point, detect that the system is out of equilibrium because we see that it's not equilibrium concentration, but there's another average concentration we find in the system. But when we gradually improve resolution, decrease the length scale R, we start to see that there is spatial pattern in this system. So it's clear that when we improve resolution step by step, there is information appearing at certain positions and at certain length scales. So this is the idea with the geometric information theory, to be able to detect length scales and positions at which we find information. So I would like to draw the system we study in both in space, x, y, and in resolution length, going vertically here. And the total information can we can divide in, to start with, in two terms. One term is the chemical information. What I said before is something that we can detect already at the very bad length, the worst length scales, R being infinity. And then we have some spatial information coming from the presence of a spatial pattern in the system, which is something that we find when we improve resolution towards the perfect resolution. And typically we will have a decomposition of the total information along length scales looking like this, that there is a specific length scale where we do get a lot of information, or we, of course we could have several peaks on that, on the improvement of resolution. In this situation, this is just schematically sort of indicating that we do have a lot of information at the length scales of the concentration peaks. I will not go into the details of this decomposition, but just mention that the local information density at a certain position x depends on the gradient of the logarithm of the concentration. So it means that the local information density detects slopes in the concentration profile, which is sort of reasonable when if we think about the picture, where in the picture is information located. We usually consider that information is located at the edges of the objects that we observe. And that is what this quantity also results in. So if you integrate this local information density K of R and X over space X and length scale R, you get the total spatial information of the system. Now we will illustrate what this information density means for this Gray-Scott model of self-replicating spots. So to the left we have the continuation of the simulation I showed in a couple of slides before. And in this simulation we look at the information density locally at a specific length scale being 0.01, which is a fairly good resolution. And what we see is what I said in the previous slide, that the information density is large at the edges of the object, of objects in the system. Now if we look at the same situation or the same simulation at a larger length scale, where we don't have the same good resolution, at this level we cannot any longer detect the single spots, but there is still some structure visible in the dynamics. And that is related to the fact that at some points in time many of the spots die out, form holes in the population of spots, which results in high information density at those larger length scales. So what I showed now was at some different levels of resolution that we do have different picture on how information is spread out over the system. And if we place this information picture in the two-dimensional space and also the space spanned by the length scale, we can also draw into this schematic picture where the physical flows or the physical processes interact with the information dynamics. The first and important, maybe, well, one very important part is, of course, that this system is driven by an inflow of the fuel. The result of the inflow of the fuel is primarily that it keeps up the chemical information of the system. It keeps the system away from equilibrium. So it keeps, in this case, a high average concentration of the fuel in the system. So the inflow primarily adds information at the very long length scales. Then there is another important physical process involved, and that is that we have entropy production due to both reactions and to diffusion. And both of those entropy processes I put on the finest levels of resolution. And the reason why I do that is that we could, in principle, model this system using a molecular picture with reversible dynamics. sort of going down below the finest level of resolution in this macroscopic picture. And in such a reversible model involving all molecules on the microscopic scales, in that model entropy would not be, or information would not be destroyed. So therefore it's sort of reasonable to view the entropy production taking place in this macroscopic description as an outflow of information going down to the microscopic degrees of freedom. And without showing any details of it, you can then define flows within, sort of in between these connections that the dynamics has with physics, between the inflow of free energy and the destruction of information due to entropy production, by introducing a spatial flow of information across space and a flow of information across length scales, where I've chosen a direction going downwards in scale, which sort of comes from the fact that the driving information capacity flow enters at the larger length scales, while the outflow or the destruction of information primarily occurs at the finest length scales. And it turns out that when you calculate this flow across length scales, in all cases I've tested so far, I mean, it's directed downwards. So it's, I mean, that it's directed downwards down at the finest levels of resolutions correspond to the second law of thermodynamics. Then the downward directed information flow at all different length scales is sort of a generalization of the second law of thermodynamics when you are not studying the system only on perfect resolution r being 0, but on arbitrary length scales. So this is summarized in this continuity equation for information, where the local change can be seen as an aggregation of information coming from the flow downwards in scale, aggregation from the flow across space. And there is also a sinc term that I will not discuss now. It's a very small term, and it's really outweighed by the large inflow of information capacity coming from the fuel entering the system. So this is now an illustration of the information flow downwards in scale. Again, the same scenario as before. And here we see that the flow from larger to smaller length scales when we are at the fine resolution level. So this means that we are observing the system very, very close to the transition from macroscopic to microscopic descriptions. Then we see that the flow downwards in scale is located at the concentration peaks. So there is a direct relation between the peaks and where we have the flow downwards in scale. And that, of course, comes from the fact that this flow transforms into entropy production when we get down to the finest levels of resolution. And entropy production is the highest at the concentration peaks, because that's where most of the chemical reactions are taking place, where we do have a major part of the entropy production. Also, diffusion contributes to entropy, but not as much as the chemical reactions. At the larger length scale, or at the more worse level of resolution, we see again the patterns before, where we do get information where we have holes in the populational concentration peaks. But here it's clear that we have a much more uniform flow downwards in scale. So the picture we get here is that information is entering, or information capacity is entering on the large length scales as the fuel enters the system. And then this information flow is aggregated when we get information being formed at different length scales, and the flow is sort of located or directed towards the concentration peaks before it disappears from the system due to entropy production in the concentration peaks primarily. And yeah, that was sort of the overview picture of the information characteristics that we have been using for this and other types of pattern-forming systems. Now I'd like to get back to our other interest in the self-replicating spots model, and that was whether we could also in other types of reactor architectures get self-replicating patterns or specifically self-replicating spots. This is an example of a microfluidics reactor. The size is 5 millimeters here, and here we have inflow of chemicals that are mixed over there, and this reactor widens to reach a much wider edge with a lot of number of outlets. So what we have here is what is called a fan reactor, where we have larger flows initially that slows down later on in the reactor. So this is a reactor that has been developed technology in the microfluidics technology in the PACE project. It has been tested for one specific type of reaction resulting in a standing wave. This has been measured using fluorescence technique. So what one has found is that there is a standing wave in the system with a peak that is quite close to the inlet. But there was no sort of pattern formation being formed in this type of experiment. What we wanted to investigate theoretically was whether the Gray-Scott type of dynamics could give rise to pattern formation in this system. And the main difference now in this setting compared to the original experiment I showed in the second slide is that in the original setting we did have an inflow of the fuel that was happening throughout the whole system, perpendicular from a reservoir in contact with the whole reactor through via a membrane. Now in this situation, all the fuel enters the reactor at one edge. And for the original model for self-replicating spots, that is a problem because then all the fuel will sort of be consumed initially at the entrance of the reactor, and then nothing will be left no free energy will be left for forming patterns later on in the reactor. So what we did test was to modify the Gray-Scott reaction by adding a precursor, U star, to the fuel, which is in equilibrium with the fuel. Actually, this is an equilibrium that is shifted far to the left. So by adding this reaction, and using U star as the component that enters the reactor, we can delay the formation of U that takes part in the reaction. And using that change, it becomes possible to get something that forms patterns. To start with, we'll see some wave patterns similar to the experiment that has been performed in the fan reactor, but pretty soon we also see that there is a symmetry breaking in this direction where we start to see the formation of concentration peaks and also to some extent the division of the peaks into pairs of peaks, etc. This simulation also illustrates some of the points with this type of reactor. What is seen here is that we actually have different characteristics along the path of the reactor. So within one single reactor, we actually sort of scan a continuum of parameter values. So one need not tune parameters exactly here, but by changing one of the critical parameters, what it will change is the position in this reactor where you will get this phenomenon. But so far this work has been purely theoretical, and with John McCaskill, who is leading the microfluidics research and experimentation in Germany, we have discussed what could be possible chemical reaction schemes that could support this type of dynamics. But that is not yet, has not really yet started. So, to summarize very, very quickly here, I mean, I described in information theoretic terms how we can characterize the pattern formation process, or at what length scales and positions we find information. We connect that information description with an inflow of chemical or free energy in the form of information capacity, and the destruction of that information due to entropy production from reactions and diffusion. There is the possibility, of course, to continue to study what happens with these flows and the microscopic description of the system, and not directly related to this, but studying information dynamics on microscopic reversible systems. In that setting, we have recently also formulated the continuity equation for information on the microscopic level of the system. But that primarily was formulated in the context of cellular automata, and it relies on, as I said, a reversible description of the dynamics. But if such an extension can be made, one can follow the information flow from the macroscopic levels down to the microscopic levels, and you can actually see on the microscopic levels how information is spread out on the microscopic degrees of freedom, so that if you locally observe the system, it will look as if information actually is being destroyed. But if you take into account arbitrarily long correlations, the information is still there. But that is sort of a different type of topic. And by that, I thank you for your attention.
Thank you. Question, please. I mean, the mechanism that you developed in order to understand the flow of information is an interesting and general mechanism, and you applied it to a particular system which has replicating aspects. Do you think the flow from large scales to small scales is possibly general, or could it actually go the other way around in other systems? And how about living systems? Naively, you would think maybe information comes from small scales to large scales.
Yes.
So that was possibility is possible.
I mentioned initially that there are at least 3 different information quantities that are of interest to study in this type of systems. And I mentioned, well, both the genetic information, but also the information from fluctuations. And so there is clearly, I mean, fluctuations going on here that will affect what type of structure you see at large length scales. So there is a flow going in the other direction as well, which is not directly captured in this formalism. But one should also, I've thought about it, I don't exactly know how to put it in the same framework. One problem is, I guess, that the flow from the microscales to the macroscale is very small quantitatively compared to the huge flow of information, because of this relation between free energy as information capacity and information. I mean, it's 10 to the 21 bits of information for a single joule of energy. But I agree. I mean, I usually have also another slide with information arrows going from micro to macro, which is something I would like to be able to capture in this type of discussion as well.
Okay.